This talk. My name is Leo, and I'm going to present Codex, which is a decentralized storage network. And this is, part of the Logos organization. All right, so the background of the outline of my talk is, first I'm going to give a quick background on why we need decentralized storage, what is the difference between decentralized storage and what we have seen in the past and what we have today. Then I'm going to present what are the ingredients to cook decentralized storage, basically what are the properties that we want to ensure in decentralized storage. And then I'm going to talk about the design that we are trying to implement right now in Codex. And so that involves several components, like erasure codes, remote verification, marketplace, metadata, and a little bit of the description of how the node works and the flow works in Codex. And finally, I will conclude. So let's start with the background. I think we are all familiar with peer-to-peer file sharing. These are platforms that have existed for a long time. I think at least 20 years ago, we already had many peer-to-peer file sharing software like BitTorrent, Napster, Nutella, IPFS, and so on and so forth, right? This started getting a lot of popularity like over 2 decades ago. However, this is not what we use today for storage. Now, before going there, I want to talk about peer-to-peer file sharing. Peer-to-peer networks have a lot of interesting properties that are interesting for us. I think the first property that is very interesting is that it's naturally resilient, right? Even if you lose a bunch of nodes in your network, you still can keep running the entire network. To give an example, when, for example, China decided to ban Bitcoin mining, on the contrary, a bunch of nodes went down and the Bitcoin network still was working and running, right? So this is one of the main properties that are super interesting for a peer-to-peer network and that are important for censorship resistant, which is one of the properties that we want to guarantee into a decentralized storage and many others. Now, the other thing that is interesting is that the system scales linearly with the number of participants, right? So if you imagine, for example, in a decentralized storage, every node or every other node adds its own storage as part of the storage that is available to the network, then every time you have new nodes coming into the network, you also gain some storage, you gain some bandwidth, and then your system scales as the number of nodes scale, right? So this is another property that is quite interesting. Now, then we have content addressing, which is also an interesting technique. It offers built-in integrity checks and tamper resistance. And what is interesting about is that the content can be retrieved even if we don't know where the location of that data is, right? So we just kind of ask someone in the network, hey, I'm trying to look for this data. Do you know where can I retrieve it? And somehow at some point you manage to retrieve that data, right? And at the beginning you didn't know where you have to go or who you have to ask. But at the end of the operation of the transaction, you finally know where you need to get the data from, and you get the data from. So this is kind of very crucial in building networks without federation and decentralization. Now, however, what we see today is that we are not using any of those software or any of those protocols to implement, as a storage system, right? And the reason for that is that when you put content in, peer-to-peer file sharing software or whatever, there is absolutely no guarantee that the data that you put here today is going to be there tomorrow. Basically, there is no guarantee that you can retrieve the data in 2 weeks, 1 month, a year, forget about 10 years from now, right? So there is this property that we call data durability that I think is crucial in order to implement a decentralized storage network, right? Data durability is actually this property that we want to ensure, and it means that when the system says you can retrieve the data in 2 years, you are 100% sure you are going to retrieve the data in 2 years, right? So what is data durability? And many times data durability is confused with availability. And these are two different concepts. I think in one of the talks today, data availability sampling was mentioned. Availability is very different from durability. So if you think about availability, for example, in the figure on the right, your left, you have a system in which, for example, you have some network issues at some point, you have some power failure, so during that time, the data is not available, but later on, the node comes online, and then the data is available again. Maybe you run out of bandwidth at some point, and so on and so forth. And you can say that through the entire year, maybe, your data was available 90% of the time, or say 99% of the time, right? So that is when we talk about data availability, we talk about this kind of thing, right? Which is different from data durability, which is when I put something in some storage or some decentralized storage, I want to make sure that if I sign a contract that this data is going to be available 1 year from now, I have the guarantee that this data is going to be available 1 year from now, all right? So these are two different concepts that are important to differentiate. Now, so I'm going to talk about what are the components or the ingredients that are necessary, or that we believe that are necessary, in order to implement a decentralized storage network. So this is more or less the list. You can go a little bit more into granularity or more in details, but basically what you need is first redundancy, any type of redundancy, but not all of them are very efficient. I'm going to talk about that later. You need data dispersal. You need remote verification, you need repairs, and then you need incentives, okay? So let me go through those one by one. First of all, redundancy. So the goal of redundancy is to increase the reliability of a system, meaning that when I lose part of the data, in this context, I will be able to retrieve that data somehow, right? And there are different types of implementing redundancy. One of them is replication, okay? Replication is super simple, it's straightforward, is I take this data and I copy it in another place, okay? So if this hard drive fails, I still have it in another hard drive, right? And if I want to be very, very sure that I will retrieve it, then I just copy it into 2 hard drives or 3 hard drives, right? And so that guarantees that even if 2 of them fail at the same time, I still have the 3rd one that is available somehow. Then there is another way to implement redundancy, which is erasure coding. Erasure coding uses mathematical properties in order to generate extra data, which is not the exact same data that you have originally. It's just another type of, that if you look at it, it's going to look just like random garbage. But that data will allow you to reconstruct the original data in case of failures. So let's go through these two a little bit more into detail. What are the trade-offs between data replication and erasure coding, okay? So basically, I think to simplify, if you want to remember in a nutshell, the difference between the two is that erasure coding is computationally expensive. It's going to take a lot of computation in order to generate those extra blocks, okay? And data replication is not computationally expensive. It's actually super simple. There is no computation. You just need to copy data. That's super simple to implement. However, data replication is very expensive in the amount of storage that it's going to take you to have a good level of fault tolerance, while erasure coding allows you to have a high level of fault tolerance with a low storage overhead. So to go through an example, if I imagine I implement a replication factor of 3. That means I have my data set, and I want to have 3 copies of that data set, okay? So imagine my data set has 100 gigabytes. In total, I will use 300 gigabytes, okay? 100 in different nodes or hardwares or hard drives or whatever. So the overhead in terms of storage is 200% in this case, okay? I need to do 2 extra copies of my data. Okay, and the fault tolerance that I have is 2, because out of the 3 copies that I have, I can lose 2 of them, right? So that's the fault tolerance level that I have. Now, if I imagine I implement another system with erasure codes, And I have parameters that actually I will explain a little bit more in detail how array coding works. But I have, like, say, 5 blocks of data. And I increase these to have 10 blocks of total data, which is 5 original data plus 5 encoded blocks. Then I have created a storage system in which my overhead is 100%, right? Because from 5 blocks, I pass to 10 blocks, all right? So the overhead in terms of storage is 100%, which is only half of the replication of the case of the replication, right? But if you look at the fault tolerance level, actually, I can lose any 5 blocks out of the 10, and I will still be able to recover the whole data set. No matter which 5 blocks I lose, I will be able to recreate the original 5 blocks of data that I have. Okay? So in this case, my my fault tolerance factor is going to be 5. Okay? So I have over the double of fault tolerance, and I use half of the space. All right? So these are the benefits that I get using erasure coding versus replication. Okay? So this is why we use erasure coding. And actually, this comes up with a lot of other nice features that I will explain a little bit later. So dispersal. Dispersal is another important part of the equation, let's say, of the system. The idea is that we have to place the pieces in physically distant, independent locations. I mean, I think this is obvious, right? You are not going to generate 5 extra blocks and put them all in the same hard drive, because if you lose that hard drive, basically you are not getting anything. But it also is important because it accelerates retrieval, right? So if you want to download the entire file, actually you don't need to download the 5 original blocks that you had stored in 5 different nodes. You actually can download any 5 blocks out of the 10 and then just recreate the original data set, right? And so this is much better because if one of the 5 nodes that are stored in the original blocks is slow or has really low bandwidth or whatever, then you are limited by that factor. But using erasure coding, you can just simply retrieve the fastest 5 blocks that you can get and then compute the original data using erasure coding. Okay? And so this is also very important because it avoids withholding attacks, right? If one of the 10 nodes is trying to act maliciously and say, I'm not going to give you the block that I have, then you say, well, I don't care because I have other blocks and I can regenerate that block using erasure coding, right? So this is another important part of the system. Now, remote verification. Remote verification is also, of course, extremely important. We are in a Byzantine network where any node can join the network and can act maliciously, right? So we have to make sure that the data that we give to the storage providers is still being stored as they promised that they will store it. And for this, we need remote verification. But we cannot simply say to them, hey, can you send us the data set that we sent you last week to make sure that you still have it? Because, you know, obviously, if we are talking about data sets that are in the order of terabytes, and you need to ask all the nodes, hey, send me all the data to verify that you still have it, that this is really not scalable at all, right? So you need to implement a system that is scalable and that still allows us to make sure that the nodes that are storing the data still have the data as they say they have it, right? So linear complexity is not good enough when we are trying to detect errors in decentralized storage. So how do we do that? We use something that is called sublinear sampling, okay? And this is, again, one of those properties that marries very well with erasure coding. And is that actually you don't need to verify the entirety of the data set. You can actually just verify a very small portion of it using sublinear sampling, and you will be very reliably capable of detecting errors or missing block in that data set. In practice, we can sample less than 1% of the data set, and we will still have very, very strong probability that the data is still available. Okay. So how does this work? I mean, I think the whole intuition here is that sampling half of the data set is much, much easier than sampling the entire data set, right? If your system needs to guarantee that every single byte of your data set is available, then you are in trouble. Because if one single node is slow or lazy or malicious or whatever, and is not answering your request, then you cannot be sure until that node answers you, right? But the thing is that because we're using erasure codes, actually we don't need to verify the entire data set. We only need to verify that half of the data set, and half is an example, it depends on the erasure coding parameters that you are using, but if we assume 50%, then you just need to make sure that half of the data that you sample is available, and you can actually do that even without sampling half of the data, just a very, very small amount. So if you look at this small equation here, where you say the probability, I mean, the guarantee that the data is available is n minus k over n at the power of p. K is the number of blocks, original blocks. N is the total number of blocks, so after expanding using erasure coding. And P is the number of samples that I'm going to ask, the number of segments that I'm going to query, right? And if you put, for example, these numbers, so K is equal to 500, N is equal to 1,000, and P equal to 80. 80 is not a large number, so I just need to sample 80 segments. We get that we can be almost sure that the data is available. The probability is 0.9999. I'm not going to count how many nines are there, but there are many. And that gives us a lot of, a very high confidence that no matter how many blocks are missing in the space, I have still enough blocks in order to recreate the original data using erasure coding. Now, repair. Repair is an important part of the system, of course. Detecting failure is not useful if we cannot repair them. The idea here is that when we detect that some data is either corrupted or missing, we can repair it. Now, however, repairing, you have to be careful with repairing. It's important to mention that when you are computing erasure coding, repairing one block or repairing 4 blocks takes the same amount of computation. Right? Is more or less the same process. And so it's the same calculation. And so what happens is that if every time you find a block that is missing, you repair it, you might be asking too much of the network. You are asking because you have to download blocks from other nodes and then calculate the new block and then ship that to another node or something like that. If you do that for every block that is missing, then you are going to be using a lot of bandwidth. So instead of doing that, maybe you can allow a little bit of slack there and say, well, maybe I can tolerate 2 blocks, 3 blocks, depending on what is the parameters of your system. And then once I have this number of blocks missing, then I repair this all in one batch, and then I use less bandwidth in the network. Okay, so this is what we call lazy repair, and this is another technique that we implement in Codex. Now, incentives. Okay, so of course, incentives are important. We are not relying on altruistic behavior here. It's important to implement a system that requires, that incentivizes rational behavior, and that is important to increase the longevity of the network and to make sure that participation is high in the network. So this, of course, is an important part of the whole system, right? All right. So in total, from those 5 properties that I presented, Codex consists of several components that I'm going to present now. So first you have the peer-to-peer node, which interacts with the Codex network. It finds and exchanges chunks of data with different nodes, right? It exposes a REST API to interact with users and apps. Then you have the erasure coding system, which is used both for redundancy and for remote verification, as I just explained. And then you have the proof of storage subsystem, which is necessary for remote auditing, which I'm going to also present in a few minutes. And then you have the consensus mechanism, which is related to the marketplace, the incentives, and all of that. So you have an EVM-compatible layer 1 or layer 2 that is in charge of hosting the on-chain marketplace, validating proof, and so on and so forth, right? And then, yeah, you have the on-chain marketplace and metadata. So let's go through these different components as we implement them in Codex. Okay, so let's start with erasure coding. I'm going to do a quick refresher over anybody, everybody who is familiar with erasure coding? Okay, like half of the room. Great. So for the rest, let me give you a quick refresher of how this works. So you have, let's say, a data set that you divide into 4 blocks of data. Okay, 1, 2, 3, 4. And then you say, okay, my parameters in these examples are going to be very simple. I'm going to be 4 for k and m equal to 3. M equal to 3 means I'm going to generate 3 extra blocks, okay, which are, again, I repeat, these are not copies of any of the other blocks. These are computed using a matrix vector multiplication in a Galois field that gives me some extra data here that will allow me to reconstruct original blocks. So I have 3 extra blocks here, and because I generated 3 extra blocks, now I can lose any, and I repeat, any 3 extra blocks in the system. Okay? It doesn't matter if those are original blocks or encoded blocks. It doesn't matter. Any 3 blocks I can lose. So as far as I have any 4 blocks in the system, I can regenerate the whole data set. All right? So that is the very basic idea of erasure codes. So if we look at this side, we lost the code, the block, sorry, number 1, the block number 4, and the block number 7, okay? And we have the other 4 blocks. And as far as we have 4, we can reconstruct the entire data set using erasure coding, okay? So this is the idea of erasure coding. So how would you implement this in Codex? Well, it's pretty much straightforward. We have the original data set that we divide into blocks of data. We decide what are going to be the parameters for erasure coding. So k, for example, in this case, is equal to 3. M is equal to 2. So n, which is the sum of k plus m, is equal to 5. And so we position these blocks into consecutive, vertically, as you can see in this figure. So this is block number 1, 2, and 3, and so on. Okay? And then you generate the extra encoded blocks, which are the orange ones that you see in the bottom. Okay? And so you do that with all the blocks until you finish the entire data set. And we also use interleaving so that if you have very big blocks, this doesn't put any problem, but the encoding direction is the same, basically. So you end up with something like this. So as I said, you have the blocks 1, 2, 3 that generates P1 and P2, blocks 4, 5, and 6 that generates P3 and P4, and so on. And then you can store this into different nodes. So in this case, you are going to store it in 5 nodes because n is equal to 5. Okay? But this is kind of a naive dispersal strategy in which you simply do a straightforward storing in the nodes. But it's not very optimal and not very efficient in many ways. So what we do is we use an improved dispersal strategy in which in each storage node, you will have a mix of both original data blocks plus encoded blocks. Okay? And what this allows is that first of all, when you want to download data sets or part of your data set, you are not going to only rely on these 3 nodes, but actually you will use all the 5 nodes, right? So you are gaining bandwidth because all the 5 nodes are adding bandwidth, right? So it's different this to this when you try to retrieve data. Also, when you want to regenerate data because you have some failure and you want to repair, here you will probably most likely have a lot of stress on these 2 nodes because they have all the encoded data, while here this is actually distributed among all the nodes, so you can ping all the nodes and they can participate in the reconstruction all equally. Okay? So this is an improving dispersal strategy that we have designed in Codex. Now, remote verification. We implement a verification system that is based on snarks. Okay? And this is to avoid sending samples alongside the proofs. Okay? As I said, it's important to make sure that the storage nodes have the data that they say they have, but you cannot ask them to send the entire data set because that is just not scalable at all. right? So you just want to say, for example, okay, send me the hash of this block of data, and that would be enough, right? Actually, it's not, because when you receive the data set, I can calculate the hash of the block and then just discard the block, and I will just have stored the hash, and then I will cheat all the time, right? So you need a system that is a little bit more complex than that. So we need to implement some kind of stealth and some kind of randomness in the system. So you say, for example, send me the hash of this block with the block hash of the current, Ethereum final last block or something like that, right? And then, in addition to that, you want to be able to actually compress those proofs as much as possible. And this is something that snarks give us, because we can actually aggregate proofs in many, many ways. Like, for example, you say to one node, okay, send me the hash of the proof of this block, this block, this block, this block, and I send you a list of 100 chunks that I want you to send me the proof. And then internally, in your node, you can actually aggregate all those proofs because they are based on snarks. And then you send one single proof that actually encompasses all the different proofs that you had internally. And then additionally, if you want, and this is something that we might want to do later on, you could also aggregate proofs across nodes in the system. And you could actually even aggregate proofs across different data sets if that was to be necessary, right? And so what happens is that now you end up with a small proof that you can store on chain, and anybody can look at the data on chain and can say, okay, the data that I stored there 2 years ago is still there, all right? Now, the marketplace. The marketplace is, where the storage requests are made. In other words, this is where storage is bought and sold, okay? And we use something that we call slots. So a data set is split into multiple slots. A slot is equal to the amount of data that goes into one specific node, okay? And so you will have data slots that are from the original data set, but you will also have slots for the encoded data, right? So if, for example, if you use the parameters 3 and 2, as I mentioned previously, you will have 3 nodes for the original data and 2 nodes for the encoded data. I thought I already explained that the dispersal actually changes that. But what I'm trying to say here is that you will have 5 slots because you need to take into account the ratio coding parameters, okay? And so, yeah, so when you upload a data set into Codex, you decide what are the erasure coding parameters that you want to use, and based on that, the marketplace will say, okay, we need n storage nodes, and then the data set is of this size, and so each one of the storage node needs to store a slot of data of this size, okay? And then at that moment, the storage nodes will try to compete and try to get this storage, those that are interested and that they have availability. They will try to get the slot in order to participate in this contract. Now, if we look at the details of how this goes, so the user do a request for storage. The marketplace broadcasts this request to the entire network. The network, of course, is composed of storage nodes. And then the storage nodes will reserve those slots if they have enough space and if they are interested in this particular contract. And then when this happens, the marketplace will signal back to the user, and then the storage nodes will proceed to download the data directly from the user node, all right? And then once they have the data, they will submit the proof that they have the data, and that means that that slot has been filled. And after all the slots have been filled, then we can say that the contract has started, okay? And from that moment on, your data should be stored until the end of the contract, which is also another parameter that you specify when you want to upload some data into Codex. Okay, to finish here, so you have metadata, of course, which is important in any peer-to-peer system. Codex uses a manifest, which stores metadata related to a data set. It's used for both the original file and the erasure-coded blocks, okay? And it's basically, it it behaves in the same way as any other block in the system. If you have questions about this, we can ask me later. So again, let's go through the Codex Flow to try to understand how the whole system, I have presented all the ingredients, all the components, all the design. So let me try to put all this together and explain how this goes into Codex. So first you have, as I say here, you have the client node, which is the node where you are going to run Codex in order to upload datasets. Okay, so first you do an upload of your file. Upload is actually a kind of confusing word because at that moment you are not really uploading anything to anywhere. It's just in the Codex kind of network. Then after this, we're going to request this, we're going to signal this to the Codex peer-to-peer network. Then we do internally what we call a request for the storage. After this, we proceed to do the ratio coding. Okay, so here we do the ratio coding internally inside the client node. For that, at that moment, of course, you already have all the ratio coding parameters. And then after you finish the ratio coding, there is a request for storing the chunk. So you do the storage request to the marketplace, which is, I guess, as I said, is a smart contract that is stored in an EVM-compatible blockchain. All right, so you do the request of the storage. After you do the request of the storage, some nodes will try to get the storage, offer the storage, and then we'll download the dataset directly from the node, from the client node. All right, and then after all the slots have been filled, then the smart contract marketplace say, okay, we already filled all the slots. Now the contract can start. Okay, and then from that moment on, then every X amount of time, you need to verify that the data is still there. As I said, we don't want to verify everything all the time. We do this at a specific frequency that we have been calculating and trying to calibrate very carefully. But then every X amount of time, the proof time system is triggered, and that means that the storage nodes will need to send proof of storage to the smart contract. And so here there is a challenge, what we call a challenge, and then the storage node will need to show that the data that they have is still there. They will hash it with something, like for example, the last block of the blockchain here, and they will send the proof to the smart contract, and this proof will be stored on chain. Of course, there is a lot of proof aggregation that happens here, as I mentioned previously, so that the amount of data that you need to store is very, very small. Okay? All right, and then I guess just to finish, I want to give just a quick overview of the Codex Client. For those that are interested, so you have, this is more or less the structure of this software, if you wish. So you have the HTTP REST API here, the marketplace driver that communicates with the marketplace contract that is probably on a get node, assuming you are running Ethereum. The EVM-compatible blockchain, it communicates with through the contract. And then here in the center, you have the core logic. You have the proving setup on the client side. You have the ratio coding module. Then you have the block store here that is that has many components like the block exchange, lib peer-to-peer to be able to communicate with other nodes. You have the data store, the local store repository, and you communicate through the network with the other nodes in the network through lib peer-to-peer. And then here you have the portion C module, the sales, the validator, and here you have the proof generation module. So this is all the things that you have inside the Codex client, and more or less for you to have a visual idea of the design of Codex. All right. Yeah. So just to conclude, yeah, we have had a lot of peer-to-peer file sharing networks over time. They have many desirable features, but they are not suitable for long-term storage because they don't offer data durability. So for that, we need a new system, which we call decentralized storage networks, that offer and guarantee data durability. But to guarantee data durability, you need a number of techniques, which are the techniques that I have presented in this talk, which are redundancy, dispersal, remote verification, repairs, and incentives. And among all, you need to implement them in a way that is very, very efficient and is scalable. Okay? So with all that, thank you very much for your attention. And if you have questions, I'll be happy to answer. Any question? Okay, if there is no any questions, then I think I will leave it to the next one. Thank you.